Okay, hi. So for this experiment, we're going to look at the standard reduction potentials and look at our results and do the calculations. So if you look on the first page of the procedure, what you'll see is a small table of several values of standard reduction potentials, which includes the metals that we studied in this experiment. So silver is here at zero point 0.8 volts. Copper 2 is here at 0.34 volts. Lead 2 is here at negative 0.13 volts. Iron 2 is here at negative 0.44 volts. And zinc is here at negative 0.76. So we'll need those numbers for our calculations. Okay. So let's take a look. Now, what I have here in part one, table one, are the three measurements for each of the um, measure of the differences in potentials that we measured. So we measured copper, zinc, copper, lead, copper, silver, copper, and iron. Now, the first thing we want to fill out here are the metals at the positive terminal. That would be the cathode. Remember, the cathode is where reduction is occurring. The metal at the negative terminal, that's the anode. Okay, so that's where oxidation is occurring. And then we'll write the half reactions in for those. Okay. So let's take a look at the first one. Copper and zinc. So when we made these measurements, we put the red lead on the copper. And if you get a positive voltage, that means that the metal that's underneath the red lead is positive. Okay. So if you get a positive voltage, which for the first one we did, those are all positive values. That means the metal that is under the red lead is the positive, and that was the copper. So we're going to write copper for that one. And then that other metal would be the negative terminal. So for that one, that would be zinc. Okay. Now, the half reaction, what you do is you come back to your original table up here and you look up for copper and zinc. So here it is for copper. That's the reduction reaction for copper. And this is the reduction reaction for zinc. But for zinc, it's a negative potential. So that means that it got oxidized. So you'll write the reverse reaction. So the zinc will be a reactant, and then zinc 2 and 2 electrons will be the products. Okay. So we come back down over here. So the positive terminal is the copper. So we write just like it is in the table. Oops. Got that capitalized there. Okay. And then for the one at the negative terminal, that would be the oxidation of zinc. So you just write zinc goes to zinc 2. A bit smaller there, sorry. There we go. Okay. Let's make this superscript, and the charges should be superscript 2, right? Okay. Same thing for the next one. We got a positive voltage. That means copper is the positive terminal and lead is the negative terminal. So whatever you get here, I'm just going to copy and paste that. That's going to go there as well, right? Because it's the reduction. The positive one is the reduction. And then the negative one would be the oxidation. So lead goes to lead 2 plus 2 electrons. Okay. Oops. Now I won't do the last one, which is the iron, but I will do the silver because the silver is a little different, right? The silver, we got a negative voltage. And so if we get a negative voltage, that means the one at the positive terminal is the other metal. So it would be silver would be there. And then the copper is over here. So essentially what's happening is if you get a negative voltage, that means the metal under the red lead is the negative one. And so that would be the copper. So the copper is the negative one. And so now copper's not getting reduced anymore. It's getting oxidized. So we have to write the reduction of silver. Again, this comes from the table on page 1. Okay. So I'm not making this one up here. I'm just like getting it from that table. I'm not referring back to it, but you'll be able to see us there. Okay. And then not sure why this one got reformatted there. There we go. So then the copper. So what I'm going to do actually is I'll just write it. Oops. Cu goes to Cu2 plus 2 electrons. Okay. I won't do the last one, but you can kind of tell it was a negative voltage. I'm sorry, it was a positive voltage. So you can tell which one is going to get oxidized, which one's going to get reduced. Okay. All right, we'll skip over this. We didn't do that part. Now, the averages, I've taken these values here. So I've taken the average of these three, the average of these three for each of those differences, and I've written them in over here. These are the averages, right? Just add them up, divide by 3. So copper zinc 1.05, copper lead 0.51, copper silver negative 0.42, and copper iron 0.72. And again, I just copied these over here. Now, here's what we're going to do. In this column right here, the reduction potential of the metal reacting with copper. So all these are reactions with copper, right? Each time we had the red one on the copper. So that means we're really looking at the reaction of the other metal with copper. So when we measure the potential for the cell, we're taking a measurement of the difference between the cathode and the anode. So for copper and zinc, copper is the cathode. So that means that copper's reduction potential minus zinc's reduction potential should be equal to this difference we got here, 1.05. So 1.05 is equal to the difference between these two. Now, in this column, what we're doing is we're letting copper be 0. So really we're saying 1.05 is 0 minus zinc. So if you write that down on a piece of paper, 1.05 equals 0 minus zinc, and solve for zinc, right? You should do that so you can see how the arithmetic works out. You'll find that zinc is just negative 1.05. Okay. And if you do the same thing with the lead, 0.51 is equal to 0 for copper minus lead, and solve for lead, you'll get that lead is minus 0.51. Now, here the difference is negative 0.42. So negative 0.42 equals 0 minus silver. Solve for 0, you get 0.42. So you notice you're just changing the sign when you do this arithmetic. Okay. Now we're going to use the actual accepted value for copper, which is 0.34. So we're just going to add 0.34 to all of these values. So if you add 0.34 to negative 1.06, you get 0.7. Let me go through this and do the calculation because I want to make sure I got it right. So 1.05 negative plus 0.34 is negative 0.71. Okay. Now, same thing. Add 0.34. and you get negative 0.17. This is 0.42 plus 0.34. That one is 0.76. And then negative 0.72 plus 0.34, negative 0.38. Okay, so there's our values right there. So now what we're going to do is come down to the next table, and we're going to list them from most positive to most negative. So just looking at these values, remembering that copper is 0.34. So the difference between copper and zinc, we ended up with negative 0.71. Okay, so that would be the standard reduction potential for zinc. So I'm going to look for the most positive one. That's right here. That's silver. Silver is 0.76. So Ag 0.76. Oops, no problem here. Let's do it right here. 0.76 is Ag. Okay. And then the actual value is 0.80. That's up in the table. Okay. Next one, next most positive one. Well, these are negatives here, right? So that means it must be the copper. It must be the copper at 0.34. So we'll put in copper here, 0.34. The actual value is 0.34. So this one's kind of a fake one. That one we can't really like say we did a good job on that one because we actually listed it at the actual value. So then we come back over here. The next most positive appears to be this one right here, lead at negative 0.17. Okay, the actual value for lead, I don't really remember, so let's come back up here. The actual value is negative 0.13. Okay, next one would be iron at negative 0.38. If you look that one up in the table, I think it's negative 0.44. So let's take a look. Yeah, negative 0.44 for iron. And then that just leaves us with zinc. And zinc, we got negative 0.71. The actual value is negative 0.76. Okay. Then you just do a percent error calculation. Remember, percent error is your value, the experimental value, minus what we call the book value or the accepted value. So the accepted value would be these ones here. Okay. These would be your experimental values right over here. So you take the difference between those two, do that first, and then divide by the accepted value, the book value. So divide it by this value here, and then multiply by 100. Okay, so let me see if I think I have those values up here. So let's do the calculation using Google Docs. So equal sign, we're going to take the actual value minus the experimental. Then we're going to divide that by the actual value times 100, times 100. And then fill down. Of course, you should get 0 for the copper. Again, that's not a very legitimate measurement because we just essentially told it to be the correct value. Okay. So these appear to be the values. Notice this one with lead is negative. It's just negative because it's less. What happened was the experimental value was less than the accepted value, okay, than the book value. That's fine to have a negative. The formula has absolute value in it, which would make everything positive. So if you want to report it all as positive, that's okay too. Okay. Now there's a couple of questions, or there's one question anyways in here, which is the order of the metals that you got the same order as what you get in the textbook? So let's see. These are the textbook values. These are your values. So if you look at it, your goes, we're going silver and then copper, then lead, then iron, then zinc. That's the order of the numbers from increasing to decreasing. And that's exactly the same order that we got here for the book values. So it does, so for this data, the answer would be yes. Okay. And then that's pretty much it. That gives you all the values. Now, I will make a point about actual data. Iron usually has the highest percentage error because it's not really pure iron, it's really steel. So there's impurities, there's other elements in there, and you don't really get the right voltage for that one. So this may give you a very big percentage error for iron. Generally, the surface is an important factor as well. So, because silver doesn't oxidize very easily, the surface is usually pretty clean, which means that the standard reduction potential is closer to the actual value. The other metals which have negative standard reduction potentials are easily oxidized. So, air and water and salt from the air will oxidize them. And so, unless you do a really good job of polishing the surfaces, the lead and the zinc won't give you really great values as either, and you'll have some relatively large percent errors. Okay, so that's pretty much it for this experiment. Hopefully, you get some decent values. If not, um, very often it just has to do with um, how you prepared the metal, and also sometimes pushing down. You have to push really hard down on the surface of the metal when you're making the measurements.